course evaluation is due to me.
Oh, really?
Yeah.
Oh. So, before anything, I would like to just answer the question that Aditya asked in class yesterday. The question was that, so like we have reduced our problem to something super simple, like if you remember, we have reduced the problem to just, like in our Maxwell algorithm, we do it in, like we use multiplicative weight update in rounds, and in each round, all we need to solve is this LP, where this is just like the average of a lot of hard constraint, right? And to solve this LP, like we actually show the explicit solution, how, like explicit way how to solve it. That is just to construct the flow such that this thing is maximized, and then just check if this term, the left-hand side, is at least the right-hand side. If it is at least the right-hand side, you're done. If it is strictly less than the right-hand side. So Aditya just said that, okay, we should be able to just conclude that the LP is infeasible, like the flow is infeasible from the original problem. And that is true, actually. And the reason is just that, so you see, if I, like, we have this LP, right? And if instead of I write it like this, like if instead of having all of this, like this constraint for each set for in the family, if I have this for everything, then this is just asking for, like, if there is a feasible flow that satisfies the demand exactly, right? And here, like, if there exists a feasible flow, then there exists such a flow. Even if you strengthen the constraint to be like exponentially many constraints. So if we look at only the LP where there are just this many constraints, it must be feasible too. And what is this LP? It's just the average of the hard constraint here. So if this LP is feasible, this one must be feasible as well. And if we conclude that this ECS LP is infeasible, then the original one must be infeasible as well. So what Aditya said is correct. Thing is just, here we can conclude that it is infeasible, but what if we would like to get a certificate, a cut itself, that is, a cut that certificate that the flow is really infeasible. How to get that? Well, this is where we use this threshold cut that I just present in class. Yeah.
But one thing that,
Please.
yeah, so, but what is the, so whatever the witness certificate, won't it belong to the C, the set of?
Not necessary, and it shouldn't be the case actually.
Shouldn't be the case because we are already checking for all these witnesses whether D of X is less than 1.
Yes.
Initially.
Exactly. Like just initially we check that the cut from the family itself is not a violating cut first. So the cut that we get from this lemma, cannot be the one from the family. Yes. Yeah.
I was saying that, like when we're embedding it, like when we're focusing on this family C, it's like we want some Q factor better, right? Like the condition to be like Q factor like less or something.
I mean, if you look at only this set from the family, if it is infeasible there, you can conclude that this is really infeasible. But if it is feasible only with respect to the guy in C, then only then you have blow up of Q. So, yeah.
So that is the guarantee of the family?
That is guarantee of the family. That is, if the total demand, like what I mean by feasible with respect to C is that total demand in the set is smaller than the cut size for every like a set in the family. Then you know that there exists a feasible flow with blow up factor, like blow up in the congestion of Q. Yeah. So like there are like two directions that one direction you get a blow up, one direction you don't get a blow up. Okay. And all right. Let me actually maybe let's spend some time on this. So what happens in expander? Let's just try to look what is going on when you just apply this algorithm on expander, right? Well, on expander, you know that the cut approximator is just a singleton set, right? And so there is no like a non-trivial cut or anything like that. And what happened in each round, right? In each round, the framework, the multiplicative framework, gives you the weight on each cut. The weight, like P, now I can write PV plus and PV minus. That's the two weight correspond to each cut. But the cut is just one node now. And then we used to say that the potential of every node will be this thing like you look at all the cut that contains it and sum this thing up. But now there exists only one cut that contains it. So the potential is just like this. Yeah. Okay. And now comes the observation, the important observation. So I claim that the weight here is going to look like this thing. So what I mean is this. Okay. So this is basically, this is from multiplicative weight update. And let's assume first that it is like this. Yeah. So that is, okay, how should I, let's see, 1 second. Let's see. Maybe let's look at the constraint. Let's look at this LP. Yeah. Let's look at this LP when this is just a node. Each of the guy in the set is just one node. Well, what you get here is just that this thing will simplify to F, this is just F out actually. So F out of V over degree of V is greater than demand at V over degree of V. Okay. All right. So what is this thing? Do you agree that when S is just a node, this is just this is just F out, right? Yeah. Okay. And note that the excess at V here is just D minus F out. So you can write this thing as and this is just going to be All right. Okay. And now, okay. So this is the constraint. You can write it like this. Okay. And let's look at how you update the weight in multiplicative weight update. You update it by something like this. So in this case, recall that. Let's look at the plus constraint here. Basically, this is your okay. Maybe I just look at this still. Yeah. This is like your. I think you can do the math, but basically the way you update it is it's gonna be this thing is gonna be PT times this times epsilon over rho, and you flip the minus sign here to this. And this is going to be FT. All right. So this is what you get in the weight update. For the plus one, and for the minus one, you will, this is for plus. And for T plus one, maybe I should write it like this, sorry. This is a time T plus 1, T, and this is for V plus. For V minus, sorry. It's going to be just symmetric. Now this is going to be this. This is T, not plus. Okay. So the reason that there is a flip of sign here, this one become here, is because, well, I kind of flip it here, right? You have minus A and B here. Yeah. You start with this constraint A at least B, but the way you update is B minus A here. Yeah. Right. So, but once you have this, what can we conclude from this equality? So, you can write a closed form of P at time t, P plus at time t. This is going to be T, P plus at time 0, from the beginning. And this is going to be the exponent, and this is a scale, and you sum this thing. So, and this is actually still, you can have this too. Yeah. but maybe from time t to from 1 to t, maybe I. This is d of fi v. Okay. Let's try to get some interpretation from here. What is this thing? For every I, this is like kind of, this is some number between like, this is some number between -1 and 1. Because, so, this is like a, first of all, this is just a residual demand, right? And now you divide it by degree, which is like, now it's a relative residual demand to its degree. The residual demand, you can say that it is always, so let's see. Maybe this is at most between -2 and 2. So let's see. Like, yeah. Right, it's between this thing. So basically, you have some demand at V, and if you send a lot of demand, like if you send out all of your demand in this round, in round I, then it's going to be 0. But if you don't send anything, like this thing going to be big, right?
Minus 1 to 1. Won't it be -1 to 1 instead of -2 to 1?
Oh, because it can be that you have demand, which is your degree. Like you suppose that you have demand like a full, and at this round you get the flow from every direction too. That amount of flow can be as much as your degree as well. So now this is going to be 2. Can be -2 as well from the same reasoning. Right. But basically it kind of tell you how much flow, how much excess do I have in this round. Yeah. It can be even more than 1, but not more than 2. Yeah. Okay. Okay, so what does it say here? It means that if in this round you still have a lot of unit of flow at yourself, and maybe you get even more from others, the potential here gonna increase a lot, like, right? It's gonna increase, like this gonna be positive, and but like basically you sum this thing up for all the round. Okay. Okay. And now,
Could you tell the definition of D, F, T, or V?
D,
F, T, or V?
yeah, dF is the residual demand. D is just this minus F out. Yeah. And Fi is just the flow that you construct at round I. The thing that you just look at every edge and send flow like from the higher potential to lower potential.
So is dFi of V equal to dFi minus 1 of V?
dFi of V equals to
dFi minus 1 of V minus
f I minus 1
minus f I minus 1 out of
no. So like the flow at each round is just independent from each other. Like you just construct the flow in each round from scratch, right?
Okay.
Yeah.
Yeah.
Yes. Okay. All right. So this is, but just imagine that you do this, like you construct the flow just like before, like at each round, you look at the potential between two nodes and send flow accordingly. And if you do that, like it's gonna define the weight like this, where like in each round you increase your weight if you get a lot of flow, and you decrease your weight if you even have less excess that is negative, right? And the same thing is gonna be for V minus T. It's gonna be this thing, and but you get minus here. So you just do the opposite, basically. Yeah. Okay. And now, so maybe to write this thing in a nicer way, actually to be more accurate, this thing is basically like at time I, at time t, is, oh, and by the way, the weight at time 0 is 1. Yeah. So you really just get this thing. Yeah. Okay. So this is basically something like, let's say that I forget, so, okay. And there are some scaling. Yeah. So here it basically says that, okay, so maybe forget this thing. Yeah. Good. And now, so, okay. Now, because, well, if you forget about some scaling here, epsilon here, and scaling degree here, like the potential of V here is going to be that something like e to the minus e to the minus yeah, I forget about all the scaling. All right, yeah. But what it says here is just that when this thing is big, like overall time until time t, when this thing is like positive, then the potential here just gonna explode. Or like when this thing is negative, this thing basically gonna explode, like explode in the negative way. So when you get like a lot of excess or like too much excess or too much deficit, you're gonna like the weight is gonna like go rapidly in both directions. Like you either go up here or you go up here. So the weight looks like this. This is like basically the hyperbolic sign. And basically, intuitively, it kind of prevent you from having too much excess or too much deficit, right? Because whenever you have a lot of excess, your potential goes up a lot, and then in that round you should send a lot of flow because the algorithm just really look at your neighbor, and if your neighbor have less potential, you send, right? So does it like make intuitive sense to you that why this should work? Like why at the end the excess at every node should be close to zero? Just because let's look at the last round. What is the last round? Like after you finish here, you set your f to be the average of all the flow that you have seen from the beginning to the end. But this thing, now the claim is just if you sum from from 1 to t, this thing, this is just f, right? This whole thing, divided by t is this, right? So the thing that you are trying to control is exactly the excess that you want at the end. Like this sum, you want to control it to be close to zero, basically. But what is this sum? It's just the excess at this node of the average flow. So that's why if you look at the average flow, the excess at every node should be close to zero. And that's all we want. Like when the average at each node is closest, when the excess at every node is close to zero, it means that the flow epsilon satisfy the demand. In the case of expander, right? Does it make sense? Question about this?
I have a question from when I was not. Can you scroll down?
Yes.
If it's long to explain, that's okay. Why is the all singleton cuts? Why is it like a just an approximated base?
Yeah. Why in the expander singleton cut are like a congestion approximator, right? So, well, you can actually prove that when you want to construct a three flow specifier for expander, that is just a star. The way to think about this is, suppose that you have an expander. Like, remember how to construct three flow specifier? One way is to construct expander hierarchy. And if you want to construct expander hierarchy on expander, it just return that, okay, the whole thing is expander and you can track everything. So that is now that's expander hierarchy.
Right.
So the three-flow specifier is a star. And now from three-flow specifier, you can build like from a tree you build the cut corresponding to each tree edge. So that gives you a singleton cut. Yes. Okay. And once you get singleton cuts here, yeah, like it's easy. It's just more intuitive to analyze things because the potential here just depends on the weight, like. Yeah.
Once we solve the NW and finally we get df of v is close to epsilon. So then what does it mean to be, so now all potentials are close to 0?
Yes. So you get that for all v, df of v is small. Let's say it's smaller than epsilon times its degree. But this is the v itself is a set in the family, like in the family of congestion approximator. So you get that this is true for every set. Maybe with a factor phi here now. Right, because your family is just singleton, so that now you get this. But this implies that f epsilon over phi satisfy the demand. All right. Yeah. So maybe you should try to, like, it has kind of similar flavor to push relabel. Like in push relabel, whenever you have excess, you try to increase your level of potential and try to push. Here, like, it's not the same at all, but it has the same flavor where when you have excess, you increase your potential. If you have deficit, you decrease your potential and try to send from higher to lower. All right. Okay. So this is basically the diagram of problem and techniques that we have seen in class. And I would like to encourage you to look at and try to revise how everything here follow in each of the arrow. Yeah. Maybe in the exam I will just pick one arrow and ask you why that is the case. Yeah. And let you explain a bit in high level how to get the arrow. Okay. But you see, like, everything is kind of interconnected. In this part, in the min cut part, not everything, like, it's like one single thing that different technique can be used to solve different things. Not much connection, but in the sparse cut, sparsifier and flow, this is really like connected to each other in the, and like there is even like there are cycles like this. So basically, some of the algorithm that I didn't teach you really just exploit the fact that you have this cycle and try to do things recursively. Like if you have this cycle, it looks like a chicken and egg thing. Like you cannot even solve anything. But we try to break the chicken and egg situation by some good recursion. Anyway. Okay. So, I would like to just mention that, okay, we have learned a lot of important techniques already, actually. And many things are just the state of the art. But I want to just list some further important problems that we haven't learned about. But basically, the technique from this class is related. And if you want to look at this problem and try to push for the state of the art, maybe thing from this class is useful. The first thing is global min cut, global edge min cut in near linear time. In class, we have seen how to solve it in max flow time using isolating cut. So if maybe you try to recall like how to do it. Or you can use local cut in mk square time. But actually you can do it in near linear time. And that is by Karger. But the techniques that he used is like some kind of spacifier together with weight update. Then there are like, after Karger showed this in 2000, it was really open how to do it in deterministic time. And just very recently, Jason Lee this year showed how to solve it in deterministic time, almost linear. And how he did it is to basically, in the graph specification step, it was randomized, the only randomized part, and he de-randomized it. And how he did that is to use things from our class, expander hierarchy, together with some pessimistic estimator method for de-randomization. Also, like we can ask, instead of edge connectivity here, edge min cut, we can ask about vertex min cut, right? Again, in class, we've seen some algorithm, like a mk square. But the best, this is fast, nonlinear, but slow when k is big. So one can do it in max flow time too. And the ingredient there is to use isolating cut or graph sketching. By the way, next semester, there will be 2 algorithm class. One is by Uy Wong. Uy Wong. He's gonna teach a class called Algorithm for Big Data, I think. And I think he might talk about graph sketching. I will teach like a basic algorithm class too for grad student. But if any of you would like, it might be easy for you. Like it's gonna be like an easygoing class, but I will actually teach this thing too. Yeah. But anyway, for vertex connectivity, this is not quite solved because one can hope for nonlinear time. Not max flow time. And this is open even for approximation. And in weighted case, the best algorithm is MN. And this is just anything below MN would be great already. Yeah. Okay. So for sparse cut, there are some open problem. So I show in class how to do expanded decomposition in this time. There is an algorithm that takes this time. It uses some variant of cut matching game, which I call non-stop version of cut matching game. Quite interesting too. But one can hope to get this time. Yeah. And if you ask about deterministic algorithm, this running time is the best known. Yeah. And the idea is to, I mentioned that cut matching game in the deterministic cut matching game can be done in polytime, but we can make it fast. And once you can make a cut matching game fast deterministically, then you can get this thing. But to get cut matching game fast, you would need to do something. And this is the thing that I said that that we kind of do this recursion in a good way. Basically, once you get one of them deterministic, it was basically before this work, everything here is fast but randomized. And once you and now in that paper, we just make this thing deterministic. And once you make this thing deterministic, everything here is deterministic too. Because everything is just connected to each other. Right. But it's still very exciting if you can do it in nonlinear time. And let me skip this. One can talk about distributed network too. I would like to mention some other problem. So about graph specification, graph specifier, I mentioned how to compute cut specifier in the randomized way. Okay? You give an expander and you do some random sampling. But how to do it deterministic? People know how to do it in polytime, actually. But can we do it in nonlinear time? That is deterministic. That is a very, very interesting open problem. But to do this in polytime, basically, you need to learn. I taught you a bit about spectral graph theory, but you would need a bit more. But there is just one paper about this that you can just read and get this result. It's called BSS. Patterson, Sinus, Trava, something, and Spielman. Okay. Okay. I have listed a bunch of other problems actually, but you can have a look if you want actually. like if you would like to think about any of this problem, I would be happy to talk to you. Like basically, I feel that you kind of given material in this class, you would, and if you are like understand everything in this class, you have like a good way to start on any of this problem. By the way, there is some other like a big open problem in graph algorithm that that is not so related to material in this class, but I would like to mention. So one is all pair shortest path in weighted graph. So if you use like some dynamic programming, you can solve it in n cube time, Bellman-Ford or something like that. One can actually get this time.